Hello, good morning, good afternoon, and good evening, everyone. Welcome to today's webinar, Simplifying High Performance RF System Design with AMD Zynq UltraScale RFSoC, Versal RF Series, and iWave RF Solutions. First of all, thank you for joining us today. We see participants joining from multiple regions, and we really appreciate you taking the time to be a part of this technical session. My name is Divya, and I'll be your moderator for today's webinar. This session is a joint webinar by AMD and iWave focused on real-world RF system design challenges and architectures using RFSoC and Versal RF boards and solutions. Here's a quick look at what we'll be covering today. We'll begin with AMD's overview of the Zynq UltraScale Plus RFSoC and an introduction to Versal RF series, covering system architecture and RF capabilities. Next up, iWave will take you through key RF design considerations for both platforms, followed by a look at the roadmap and extensive RF SOM and solutions portfolio. We'll then move on to the software features and capabilities together with the applications supported and some interesting real-world case studies. We'll conclude with a Q&A session where we'll address your questions live. Throughout the webinar, you're welcome to post your questions using the Q&A panel. We'll try to address as many questions as possible during the dedicated Q&A session at the end. If we are unable to get all questions due to time constraint, our team will follow up with you after the webinar. With that, let us dive in without any further ado. Over to you, David. Please take control.
Thank you, Divya. As I get started here, I wanted to just introduce myself. I'm Dave Brubaker. I'm the product line manager for all the RF products at AMD, formerly Xilinx, and I've been managing these products since 2018. So today I'll talk very briefly about the Versal RF series, and then the Zynq UltraScale Plus RFSoC, and then I'll talk a little bit more about Versal RF. But as we get in, the first thing I want to point out here is we do have limited time today, and there's a lot of information on the Versal RF, and I think there'll be a lot of interest here on it. So recently I did a presentation, a webinar, which you can view on demand at this particular link here at the bottom. So go ahead and you write that down as I talk. And there's a lot more detailed information on performance and the product itself, so you can go take a look at that here. We just don't have enough time today to dive into that amount of detail. So I'll go ahead and get going on this slide. So as I mentioned, I'm the product line manager, so I manage the products for the Zynq UltraScale RFSoC, and those would be the typical products which we have here, which go from backwards in this particular group here. That would be the RFSoC Gen 1, the Gen 2, the Gen 3, and the DFE. These particular products are all in our 16 nanometer process node and based upon the Zynq UltraScale Plus FPGA fabric. So the first product was released in 2018, and it went to an input ADC bandwidth up to 4 gigahertz and an output DAC bandwidth up to 4 gigahertz. The maximum sample rate on that part was 4 gigasample. It was very successful, particularly in the wireless market for the 4G and 5G early deployments. So it's been very successful there in the wireless market. We then released essentially a very minor revision to push the input-output bandwidth to 5 gigahertz. And then we did a more major upgrade to the device in 2021 where we pushed the input-output bandwidth up to 6 gigahertz. And then the ADC went up to 5 gigasample, so constantly improving the input-output frequency range and the sample rate. And then we did a very interesting part called the Zynq RFSoC DFE for digital front end. This is a wireless specific part. In other words, we actually took the hard IP that customers would normally implement in programmable logic, and we hardened it so that it would reduce the power consumption in the area of the device. So the Zynq UltraScale Plus RFSoC is actually optimized for the wireless market and can support a 8T8R remote radio head with an O-RAN interface, and I'll show you a picture of that. So after that, we launched our Versal series, and I'll talk a little bit about AMD Versal adaptive SoCs. But now we're going to be working primarily from this point forward on the Versal RF series. We actually are doing engineering samples right now, and I'll go into a lot more detail on what that product is capable of in the next couple of slides. So I'll go ahead and move on. Now, I did mention this, but the applications for Versal RF and, in particular, Zynq UltraScale plus RFSoC are pretty varied. We go everything from wireless. That's probably one of the largest markets of the top markets, okay? And we support everything from remote radio heads to millimeter wave IF transceivers, okay? So very successful in that market. It's also very successful in the aerospace and defense market for things like MILCOM, phased array radar, and electromagnetic spectrum operations. And then we also support, satellite applications, particularly earth stations, high-speed testers like oscilloscopes, and believe it or not, we actually even support the remote PHY network for DOCSIS cable network. So very wide range of applications we support. Now, this is a kind of a high-level architecture diagram of the Zynq UltraScale plus RFSoC. So again, the first set of products we have. And this shows basically at a block diagram level what's actually in the device. It's kind of a cartoon picture. But you can see that we have a processing system in the Zynq family. We have quad A53s and dual R5s. Of course, we have dedicated memory controllers. We have PCI Gen 3 or Gen 4. And up to 25 gig transceivers, okay? And we do have a 100 gig Ethernet IP to interface through the GTs here. Now, when you get right down to the programmable logic, that's what adaptive SoCs are known for. That is kind of let's think of it as a sea of adaptable logic that you can program any way you want. Of course, we have DSPs, we have system logic cells, and other functions. But within that programmable logic, we have hard signal processing blocks. So we have an SDFEC, okay, this is a soft decision forward error correction. That's actually in the Gen 1 through Gen 3, okay, and it's a hard block. And the reason we put in hard blocks is it reduces the power consumption and area for that specific IP. Now, when we went to the DFE part, as I mentioned, it's a wireless specific part. So we had additional hard IP in that particular product, which included an additional digital down conversion, digital up conversion stage, crest factor reduction, digital pre-distortion, and including an IFFT and PRATCH IP. So these functions are very wireless specific and then used to optimize the power and area for that application. Overall, we got about a 40% power reduction for the similar performance with the RFSoC DFE as it would have taken to implement it in the Gen 1 or the Gen 3. Okay, so with that, I'm going to kind of move on. Now, I just wanted to give a picture of how the Zynq UltraScale RFSoC kind of gets put together and also the Versal RF. And this is an example of the DFE. Okay, so it is the radio unit. And in that particular application, we would have through the GT applications, the GTYs, the 25 gig interface, we would have an ORAN, a CIPRI or eCIPRI interface that would come from, for example, a distributed unit. And then we would have the ORAN IP actually implemented in the adaptable logic fabric. And the reason we did that is when we actually did the design, ORAN was still changing. It was not fixed. It's even, I would say problematic today in terms of, interoperation and things like that. So you need some flexibility. But at the time, the standard was still changing. So we implemented that all in adaptable logic. But you can see these light gray blocks are the actual hard IP, and they're set up so that they can go through the data path. But in reality, at any point within the system, you can go from the adaptable logic into the hard IP or out again. So you can actually add your own IP, very flexible configuration. And this was actually quite successful with the RFSoC DFE so that we carried it forward with the Versal RF series in terms of the hard IP concept. So typically, as we have here, as we shown earlier, the ADCs and DACs would be on one side of the device and the GTs would be on the other side. And you kind of have a natural data flow from ADCs into the distributed unit or from the distributed unit into the DACs. Okay, and of course we do have the quad A53 in this particular application, which does a lot of housekeeping. It does some digital pre-distortion and things like that as a function. So it's a complete 8T8R radio on a single chip. Okay, so with that, I want to move on to the Versal product. So we'll leave the Zynq UltraScale Plus behind. Now the Versal is, let's call it the next generation from AMD's adaptable SoC product line, and it went from the 16 nanometer node to a smaller node, typically 6 or 7 nanometer. And the architecture is different. The programmable logic's a little different. We have a different DSP, we call it a DSP58. But probably the most significant difference between the Zynq UltraScale Plus and the Versal is the addition of what we call AI engines, for adaptable intelligent engines. They are really a vector processor. And when you look at this upper area here, it's a two-dimensional array of vector processors. And this particular one is actually the original one that we used on the BC1902, and it's really a vector processor that's optimized for signal processing. So it can do FFTs really well. It can do beamforming. We use it for a lot of matrix multiplication, filters, and things like that. But it's programmable in C and flexible, in the sense that you can adopt it for different functions and actually more power efficient. Now, the next thing, we of course now still have a processing unit. It's a dual A72 and a dual R5. It's about the same processing power as we had on the Zynq. And then the other key IPs in the Versal portfolio would be the PCI Gen 5. That's available. We do support LPDDR5X, so the fastest DDR5 interface. And now we actually have 32 gig and 56 gig transceivers, again, with 100 gig, and we even have a 600 gig MAC available. The other thing that's a little bit different on Versal is we have a programmable network on chip. This allows you to route data around the chip without going through the programmable logic. So for example, you can come from the DDR right into the AI engines or the PS, and it gives you some flexibility and also guaranteed bandwidth between points on the device. Now I'm showing the data converters on the right here again. Again, we have ADCs and DACs, and they go up to 32 gig sample, and for the ADC and 18 gigahertz on the RF input output. I will actually have a picture, a little more detail on that in a minute. So the other thing is you can see the hard IP that exists here. So this hard IP is different than the RFSoC DFE. It's more optimized for the general purpose market, not a wireless market. And so I'll go into those IPs in a little more detail. Okay, so let's go ahead and move on to the next slide. So I wanted to talk a little bit about the ADCs and DACs because, of course, that's a very key part of it. So we have ADC and DAC tiles. So what I'm showing here is what we call quad tile. All of our ADCs and DACs are implemented in tiles. This is not a chiplet technology. The Versal RF as well as the Zynq are all implemented on a monolithic piece of silicon. But we actually, a tile just represents a physical area on a chip, and we have 4 ADCs in that tile. But we also have other IP. We typically have the usual digital down conversion, which includes decimation and mixing. And then we run these ADCs, each ADC at 8 gigasample. So within this ADC tile, there's 4 ADCs running at 8 gigasample. They're 14-bit with calibration. And the bandwidth is DC to 18 gigahertz at minus 3 dB. Okay, so we do spec our bandwidth at the 3 dB point. And within this tile, it's all hard IP, and the interface goes into the programmable logic. We do have a wide enough pipe on this interface into the programmable logic to feed all 4 data converters at 8 gigasample into the programmable logic. Don't really recommend that because then you got to process it at the FPGA logic speed. That's why we have this hard IP here. Now, the thing you'll notice here is we have what we call a hard channelizer IP. And the channelizer is an IP function we also have in the programmable logic, which I showed on the previous slide. So there's actually 2 stages. This is what we call the first stage. And what it does is it just breaks down an input high speed, high data rate signal into lower data rate streams. So you can kind of chunk it into smaller groups of bandwidth. So if the ADC here is running at 8 gigasample, we can take this hard IP. It will accept that 8 gigasample stream and break it into 4 or 8 streams. If you break it down into 8 streams, it would be 8 1 gigasample streams that could flow into the programmable logic. And then you could do additional channelization within the programmable logic. So this allows you to take a very wide bandwidth and break it down into various channels to quickly determine where your energy is. So that's the channelizer. We'll talk a little bit about more about that when we get to the channelizer. Now, when we look at the DAC, we have a similar architecture. There's 4 DACs. Each DAC runs at 16 gigasample and again goes from the DC to 18 gigahertz, okay? And that's 3 dB. We have an inverse kind of a structure for the DAC in terms of the digital up conversion and an inverse channelizer, okay? So those are the individual tiles. There are more than one tile on each chip, and we'll go over that in a minute. But the key points here is that within these tiles, we have the IP, the hard IP to process it down at lower rates as you go through it in terms of the basic frequency conversion and decimation and interpolation. And we also have, other features like fast frequency hopping and things like that, which exist. Now, how do we get to 32 gigasample? Okay, that's kind of the next question. And for those of you who are familiar with the Zynq UltraScale plus RFSoC, you know that we time interleave 2 of the ADCs, where what we do here is we actually time interleave 4 ADCs to get to 32 gigasample. So in that case, you actually have 1 32 gigasample per tile, okay? And again, it goes from DC to 18 gigahertz. These parts are not configurable at runtime, or even when you build your FPGA design, you have to order these parts separately, okay? They actually are in slightly different packages, although they have a compatible footprint. So this shows our 4 main SKUs in the Versal RF series. We have a 16XX family, which is a 1602 and a 1652, okay? And we have a 1902 and a 1952. At a simple point, the 1902 and the 1952 have about twice the DSP processing capability. So it goes from 50 tops to 80 tops, tera operations per second. So it's a much larger device. And then the other thing is that if you look at the real key differences here, the 1652, as we have here is the 52, has actually 4 32 gigasample ADCs, where the 1952 has 8. So it has twice as many ADCs capable. Now, these are the basic the basic structure of the various SKUs. They are limited in some devices and package outlines for not all the ADCs and DACs are bonded out. But you can see we have a 16 by 16 design, and that 16 by 16 is the 8 gigasample, so the quad ADC. And then we do have the 8 DAC and 4 ADC variant, and then the 16 DAC and the 8 ADC at 32 gigasample variations. So those are the key parts we have in the Versal RF series. So just talk quickly about the hard IP. These are the hard IPs that we have on the device. FFT, very capable device. It goes at 4 gigasamples per second streaming. And this again is one block. Okay, so we have multiple blocks within the chip. I talked about the channelizer. We have actually, as I mentioned, 2 channelizers. The first one is in the ADC and DAC tile. The second one is actually in the PL, and we have quite a number of those in the PL. So once you get into the PL, you can continue to go through channelizers and break your input signal bandwidth into smaller and smaller bandwidths, but again, never use a DSP. Now, the LDPC decoder, we support 5G, Wi-Fi, and space codes, including the DVB S2 and the S2X codes. This is actually a derivative of the SDFEC that we had in the Zynq UltraScale plus RFSoC, but we only do decoding, okay? But the addition is you get these DVB-S codes. And the last IP is what we call the Versal polyblock. It's essentially a large array of polyphase filter blocks that you can then connect in a variety of ways. One of the key IPs you can implement with it is an arbitrary sampler that goes between 1 and 2 I've kind of buried it here, but it's got about 1 hertz of frequency accuracy. Okay, that particular IP is only available on the 1902 and the 1952. But the key reason I wanted to mention this, the reason we actually use this hard IP is it saves up to 80% or sometimes more of the power to actually implement that IP. Now, when you do that, it only does that IP. It's not as flexible anymore, but it does save power. So we've tried to include IP blocks in this hard IP format that are very common use blocks for the markets we're looking after. Okay, so just as a quick kind of summary of what you can do with this part, if you added up all the DSP processing and the LDPC decoders that are in the 16XX, the 1602 and the 1652, it would take about 4 VU13Ps for the DSP count and the LUT count. In addition, we have a system on chip device with a AI engine block, and that would be, and the smallest part we would have would be something like the VC1702. In addition, we've stuck in RF device in terms of a 16 by 16 RF device that transmits it up to 18 gigahertz output frequency. And all of that is crammed into one device. Okay, the 1602 or the 1652. We have 2 package sizes. We have the 37.5 millimeter square and they have the 47.5 millimeter square package. So right away you can see, from 13,000 square millimeters to either 1,400 square millimeters or 2,200 square millimeters, a huge size reduction. And that is the key swap, size, weight, and power advantage of this particular part. So next, I want to talk about, the kind of the overall concept of the Versal RF. I've already talked a lot about the hard IP. It reduces your power consumption and is extremely efficient, but it does a one IP, and when you use that IP, it's very efficient. And as I've mentioned, these IPs are common IPs that take up a lot of area and computation within the typical markets we serve. We did have the AI engine. It's actually more flexible than the hard IP and not quite as power efficient, but it's there as another type of processing capability. And lastly, we have the programmable logic in terms of the FPGA fabric, the LUT and memory, and also the DSPs, which are the most flexible and allow you to configure your solution and optimize it for what your needs might be. Say, for example, changing mission profiles or different unique applications you have. So the Versal RF has a real balance between the type of compute that optimizes, power efficiency and DSP compute in terms of TOPS, but maintains the flexibility so you can customize your solution. So I have one more slide and I'm going to pass it on. We're talking about Versal RF series. It's here. We actually are shipping, what we call ES1. We will do a production mass set later this year, but we are shipping that today. The key advantage is the high resolution, high sample rate, and frequency range that this operates over. Of course, I talked about the massive DSP compute, and that's as a result of the hard IPs. And lastly, I talked a little bit about the size, weight, and power optimization. And so, again, very key part. We're very happy about it. And if you need more information, what I would say is you contact your local AMD representative or actually check out the webinar that I promoted on the first page. So with that, I'm done and I'm going to hand it over to Pradap. So I'll go ahead and take control of that.
Thank you, David, for a very insight about Versal RF and RFSoC devices. Let's quickly go through key RF design consideration. Before that, let me introduce myself. Myself is Pradap Raj, Associate Director, FPGA System on Module Division in iWave. And I've been working with iWave for 20 plus years and in both hardware design and system design. So with this introduction, let me quickly go to the key design consideration we need to take care while designing the Versal RF or RFSoC based boards, starting from circuit schematic, what are the pre-layout preparation we have to take care, what are the layout design consideration we need to take care, and what are the post-layout analysis we have to do. Let us quickly go through. So first step of any board architecture is to estimate the power. Once we have the board architecture is ready, we need to estimate the board power estimation. So when we design a board based on the RFSoC or Versal RF based devices, so the major part of the power comes from RFSoC itself, SoC itself. So the estimating the SoC is a critical one. And to ease the SoC power estimation, AMD provides a very useful tool called Power Design Manager tool. So by giving the very simple details like basic device details, speed grade, and what is the ambient temperature the board expected to work, and also filling the basic resource utilization details, we can get the power requirement from this tool. So if you have the Vivora design, you can easily fill the power resource requirement details. And if you don't have the Vivora design, you can directly go to the each section and fill in the resource details and get the output power. So this provides a complete power output requirement of each power rails. Not only that, it also provides the complete decoupling requirement for each power rail. So this tool is very useful tool to estimate the power for the RF and also it supports two two type of power rails. We can select whether minimum power rail or full power management rail. So when we select the minimum power rail, it will optimize the power and provide the very less number of power rails so that we will have the cost effective, space effective design. Wherever we require the full power management, whenever we require full control over the each power, and at that time we can select the full power management option so that we will have the full power management control. So once we calculate the RFSoC power and we add to our board power, the next important one is selecting the VRMs, voltage regulator modules. So for the RF application, selecting the VRM is a very critical one. So for leaving the digital part apart, for the RF power rails, we recommend to select the ultra low noise LDOs with high PSSR value and low VRMS value so that we'll get the good RF performance. When some powers require very high current, then we also can use the high efficiency switcher so so that we'll get the higher power and still we'll get the better performance. And once the power design is ready, the other key parameter for the RF performance is the PLL design. So for Versal RF and RFSoC, the internal RF ADC and DAC tiles are structured as tiles. So starting from 2 tiles all the way up to 8 tiles, based on the devices, it varies. And each tile supports 2 or 4 RF channels. So when we design an PLL, so we have to provide the sampling clock, PLL clock to each tile. So we can give two options. Either we can use the external PLL or the internal PLL. So Versal RF and RFSoC devices support both the options. When we require a very high performance requirement, we can use the specific high performance requirement. We can use the external PLL and give the PLLs to each tiles. Or most of the other applications, we can use the internal PLL itself. When we use the internal PLLs, so we don't have to give the high frequency PLL externally. We just have to give the low frequency reference clock to the center tile and the internal PLL it can distribute the clock to all the tiles. So when we select the external PLLs, we can use the TI's LMX or unlock devices ADF series PLLs for external PLL. And another important feature RFSoC Gen 3 SOCs and the Versal RF has is the clock forwarding feature. So as I mentioned, so when we when the RF channels are structured as the tiles and we have to give the clock to all the tiles, then when we use external PLLs, we have to use multiple PLLs. But this internal clock forwarding feature, when we don't have to use the multiple PLLs. We can give PLL only to the center tiles, and it can be internally forwarded to the all other tiles, and still we'll get the optimum performance. So this is a very good feature, and it's supported only in RFSoC Gen 3 devices and Versal RF devices, and it is not supported in the Gen 1 and Gen 2 devices. And once the PLL design is done, so the PLL placement is another key thing. So we have to place the PLLs very close to the RF ADC or RF DAC pins, so that we will not have the PCB insertion loss and we will not lose the power. And also all the PLLs has to be AC coupled and the PNN skew has to be very minimum. Once the PCB circuit schematic is ready, the next thing is the layout. So before moving to the PCB layout, the first important thing is we need to prepare for the pre-layout, and in that first important one is the PCB material selection. So for any RF board design, PCB material selection is one of the crucial one for the performance, because of the higher frequency of operation up to 18 GHz for the Versal RF and 7 GHz for the RFSoC. So selecting the PCB material is very crucial. So select the material with low decay value so that you will have the faster signals. And low decay means decay is always inversely proportional to the signal speed. So when there is a low decay, you will get the faster signals. And also when there is a low decay, that phase widths are increased so that you will get the better impedance control. The other important parameter is the loss tangent, DF. So it is recommended to use the very low DF supported material, 0.001 to 0.005 is a preferred one. Even for if it is a 18 GHz Versal RF, even less than 0.002 DF is preferred. So when there is a low DF, then what does that mean? So that we'll have the less signal loss over the transmission line. So low decay and low DF is one of the key parameter. And not only that, we also have to see the stable and flat decay DF performance over the different frequency of operation and the temperature variation of the material. So these are the key PCB material selection parameter. So once the PCB material is selected, and we also have to select the copper roughness where the traces are signals are going. So the copper surface roughness is another critical one. So we have to select the low roughness copper so that it will help reducing the conductor loss due to skin effect, and it will maintain the signal integrity. So what does that mean, skin effect? So when the dielectric is attached to when the copper is attached to the dielectric, so it will have the roughness, mostly because of the bonding, the manufacturing bonding. Intentionally, the roughness is made. So when there is a roughness, and when we use the high frequency signal over the traces. Usually the high frequency signals are tend to transfer in the edges of the traces. So when there is a roughness in the edges, so the signal has to travel longer path. Since it has to travel the longer path, there will be a signal loss and it will have the signal integrity issue. So when we use the low roughness copper, there won't be any much signal loss because there is the overall signal path length is reduced. So we will have the better signal integrity. And also here some of the example PCB materials given for high-speed RF applications. Once we finalize the PCB material, next critical one is the finalizing the PCB stack-up. So it is recommended to work with the PCB fabricator very early stage itself to finalize the PCB stack-up. So that we'll have the better control over the PCB layout. And when we ask for the PCB stack-up, we have to recommend request to get mechanically spread glass weave type of material for the stack-up. So example is 1035 or 1078 are similar mechanically spread glass weave type we have to use so that there won't be any fiber weave effect. So what is the fiber weave effect? So normally the 1080 is a standard glass weave. So when the glass weaves are bonded, it will be the weaves will have the gaps, and usually the gaps are filled with the resins. So when we route the RF signals on the path, so take example when we route the RF differential signals P and N, and if you take the RF signals, the decay of the glass weave dielectric is different and the decay of the resin is different. So when we route the signals over this uneven space, so one signal tend to travel faster and another signal tend to travel slower. And this will create a timing mismatch and it will create this signal integrity issue. So to avoid that, we have to use the mechanically spread glass weave where the weaves are very tightly coupled and the resin content is very optimized so that you will have the stable decay DF performance over the full routing path. Also, to further improve the signal performance, it is recommended in the final layout, in the final panel design, we have to rotate the 10-degree the panel so that even if there is a mismatch, if you rotate the panel by 10-degree, it can match the decay stable decay DF performance. So here, once we have to request the stack up using these class V types and the RF signals to be routed in 100 ohm differential in the PCB so that we have to request the fab vendor for the trace width spacing. And also when we have the power layers to make sure that to get the higher thickness copper foil based power layer so that we have the higher power capacity. Here we have shown some example stack up where you can see the RF signals are routed in the paper 1035 or 1078 kind of a glass V type. And also it is recommended all the RF signals are sandwiched between the ground layers, adjacent layers, so that there will be a proper signal return path. And another important thing is, when we route RF ADC and RF DAC signals, so it is recommended to use a different layer, one layer for ADC signal and another layer for DAC signal, so that we will not get any aggression from the other pairs. So once we have the PCB stackup is ready, before moving to the layout, we have to do the pre-layout SI. This is required because to achieve the optimum performance and the target loss value, we need to tune the not only the trace width spacing, and also we have to tune how it is routed. The overall pattern has to be tuned. Like, so we have to take care while routing what type of guard trace has to be used and what length, what thickness of the guard trace has to be used, and what is the via stitching we have to use, and what type of antipad size we have to use. So these things we have to tune it and simulate it and make sure we get the secured SI performance before proceeding to the layout. So to do that, we can use the EDA tools like ANSYS iWave, Cadence Integrity, Keyset ADS, Mender Heplinks, etc. So make sure to do the optimization and get the better SI performance before moving to the layout. And this has to be done for each routing layer. So wherever the layers you are routing the RF, do the optimization at least for one pair and make sure the SI is better SI performance is maintained. So once the pre-layout preparation and everything is done, then we are going to the layout preparation. So leaving the digital part apart. So the layout, the key thing we have to take care is the placing the analog and digital circuit and completely separately, so that there won't be any EM interference from digital circuit to the analog circuits. And when we place the regulators, VRMs for the RF, place the RF rail regulators near to the RF rails so that we'll get the better performance. And also make sure the VRM designs and its capacitor are placed very closely. And similarly, the RF PLLs also has to be closely placed to the devices so that you will not have the power loss in the PLL line. And another one key thing is when we route the RF ADs and DAC lines, it is recommended to route as a weakly coupled under-room differential lines. So what is weakly coupled? So normally we use tightly coupled for the high-speed interfaces. So when we use the tightly coupled traces, so that there is a more power are concentrated in the edges of the traces and it will affect the performance. When we use the weakly coupled, it is mostly the PNN lines are relying on the ground layer than the PNN intrapair, so that it will have the better RF performance. So it is seen up to 10% of the SI can be improved when we use the weakly coupled differential strip lines. So once the power design is done, and also we have to take care the clock designs for the synchronization. So RF, most of the applications where RF channel has to be synchronized either within the single chip or within the multiple chip, because the beam forming kind of application, there will be a multiple channels are coming and all channel has to be synchronized. So the multi-chip and multi-tile synchronization is another critical parameter we need to consider while designing the PCB layout for our RF clocks. So to do that, yeah, all the clocks we have to generate from the common synthesizer so that it all are synchronized with the single clock. And when we use the multi-board synchronization, we need to have a external sync clock running across the multiple chips or multiple boards, and it has to be synchronized. And for multi-chip synchronization and multi-board synchronization, we need these are the key important RF clock signals. So analog sysref, PL sysref, and PL ref clocks are very important. So it has analog sysref as a dedicated pin for RFSoC and Versal RF. So we have to connect the clock to that, and the same clock value has to be connected to the PL sysref as well. And PL ref clock has to be a division of these clocks. So when we route the uh, signals, we have to take the delay matching for all RF channels to get the synchronization. So all RF ADC and DAC channel has to be delay tuned within 1 picosecond, and in that consider 0.5 picosecond for PCB and 0.5 picosecond for the manufacturing differences. And between the interpairs, you consider 4 picosecond. And RF PLLs also has to be pin and skew for the RF PLL also has to be less than 2 picosecond. And to do that, 2 picosecond or 1 picosecond level delay tuning, we have to use the 3D EM-wave simulators to have the exact delay tuning. And whenever there is an external resistor or the decoupling capacitors are placed, both PNN has to be uniformly patterned in the layout. And also RFSoC has the dedicated calibration resistor of calibration resistor pin. So we have to connect the 2.49K to that resistor. And finally, once the layout is done, we have to do the complete post layout simulation to make sure are the insertion loss, return loss, differential crosstalk, near end crosstalk, far end crosstalk, and trace impedance, everything is within the target. And also to the PDN and IR drop analysis to make sure the power integrity of the board. And if needed, do the decoupling capacitor optimization also in the post layout. So let's quickly go through the iWaves RF design parameters. So for what are the key RF design blocks? For the RFSoC or Versal RF, so what we need the power distribution, digital power distribution, RF power distribution, and RF PLL clocks and distribution, and another digital PLL clocks distribution, and RAM and flash memory for the booting and the application. These are the fixed blocks. And other thing is analog front-end design, which will be mostly application specific and baseband connectivity. This also based on the application specific, based on Ethernet or PCI. It will vary based on the application specific. So, but the center, these blocks are fixed blocks. So to ease the customer design, so we build the system on module to cover these fixed blocks so that customer don't have to worry about the fixed block in their design, and they can worry only about the RF front-end design and the baseband and other connectivity design. So with this, yeah, we have the complete system on module portfolio for RFSoC starting from Gen 1, Gen 2, Gen 3, and the DFE, which is coming soon. We also have the mill grade and mill grade SOMs are coming soon. Not only that, we are also coming up with the Versal RF series in the next quarter, where we use very high speed dedicated RF connectors for the RF ADC DAC, which is going up to 18 gigahertz speed, and also the digital circuit, digital connectors. And yeah, I missed one more thing. So all these system on modules are compatible, so that when you design a carrier card, you can interchange any of these modules and use it in the single carrier card. So that is another advantage we bring in when we have the system on module. Similarly, for the RFSoC, all the variants we have for the SOMs, and for each RFSoC, we do have the development kits and in the PCA form factor. And we do support 3 UPX systems for our RFSoC modules. Not only RFSoC, we do have support for other AMD Versal based forms also, starting from Versal Gen 2, Versal Prime, Versal Premium Gen 1, Versal Premium Gen 2. So we support all the Versal modules also, and the low to mid end, these variants are completely pin compatible SOMs, and the same way the high end, all these variants are completely pin compatible SOM. Not only Versal, we also support Zynq UltraScale Plus, starting from ZU1 all the way up to ZU19 SOM, and SOSA aligned PCI VPX cards, both payload and switch load profile, and smart NIC solutions for 100G and 40G. Also, we support vectors and Kintex-based system on modules, which is also fully compatible, and we also have the SOSA aligned 3 UPX and PC cards for that. Not only that, we do have the military grade and space grade SOMs, starting from Zynq UltraScale Plus, ZU19, and RFSoC 4948DR, and Versal Edge space grade SOM, and Versal AI Core space grade SOM. It's coming soon. So with this, I hand over to Abdul. Thank you.
Thank you, Mr. Pradap. And hello, everyone. My name is Abdul Ahad. I'm working as a project manager taking care of software and FPGA development at iWave. Let me begin with the software features and capabilities of the RFSoC. These features will be extended to the Versal RF series SOM modules, which will be supported by iWave. Let me begin with the iWave deliverables. This is the standard deliverable structure. So we provide a BSP build tool, which will eliminate the need to use the command line interface for building the BSP. It has a one-click interface for initializing the host environment, and it also supports different variants of the AMD SoC. Then we have the FPGA designs. We have a MTS design, which can or multi-board synchronization. Then we have a BRAM plus PCI based design, which is used for data acquisition and transmitting to the host PC. Then we have an RF analyzer design, which is used for RF validation, and IBER design for transceiver validation. We also provide a PS only design, which can be used as a starting point for any custom development. So this is the PCI host design block diagram. Here we use a QDMA based PCI IP with custom wrapper for transmitting the data through PCI to the host PC. We can also use a DMA based application to store the data on the onboard storage, and the interpolation and decimation feature can be used to reduce the sampling rate to match the PCI bandwidth. Next up is the MTS multi-tile synchronization design. So here we are using an external 5 megahertz. So external 5 megahertz for synchronization. And we use two boards in master slave configuration, where one board will initialize the ADC and DAC play and capture. We can observe the synchronization on the right side. The ADC capture can be moved to the PC, and we can visualize them using the Octave tool for validating the synchronization between multiple ports. Then we'll cover some of the real-world test case studies. So mainly the application for RFSoC products are in radio telescope, rugged SDR, quantum computing, electronic warfare, phased array radar, and test and measurement equipment. So let me explain some of the test case studies, starting with the SDR with GNU radio. Here we are using the iWave's RFSoC board to capture the data from the ADC, and we are moving the data onto the host PC using the PCI interface. And the GNU radio is running on the host PC for visualization and processing the signals. The GNU radio provides a very useful GNU GUI interface, which can be used for processing the data and for visualization purpose. Next case study is radio astronomy. Here we have the antenna station where all the data is captured, and then the data is moved onto the data center through high speed transmission. And using the RFSoC in the radio astronomy, so all the data is captured from the antenna and moved on to the RFSoC. On the RFSoC side, we can do some pre-processing before transmitting the data over the Ethernet or 400G Ethernet or InfiniBand over to the data processing center. And GPUs are used mainly for the processing of the data, the image data that is captured from the cosmic signals. The RFSoC and the FPGA SmartNIC does not replace the GPUs, but they offload some of the tasks from the GPU to the RFSoC board. Then we have a quantum control unit, quantum computing control unit. Here the RFSoC board will lie between the host control and the cryostat. So the qubits will be residing in the cryostat, and the researchers can use the host control using the quantum kit for writing the algorithms. And the data is moved onto the RFSoC board where we can run Quick or some other software stack for quantum computing. The master sequencer will generate the data based on the Python code which is generated from the quantum kit. And the pulse generator will generate the data for manipulating the qubits in the cryostat. And the readout DSP is used to read back the signals and validate the qubit states. Then we have electronic warfare, starting with the radio warning receiver. Here, the RF front end will capture all the data and move it to the RFSoC board. And the ADC will digitize and channelize the signals and run the pulse detection in the FPGA core. The data is moved on to the ARM core where the threat detection library is running. And then the signals can be used for countermeasure triggers. Next one is DRFM jammer. Here we are using the wideband signal for capturing all the digital signals. And then inside the FPGA, we are using the modification, delay, or Doppler shift for the jamming purpose. This data is transmitted back through the DAC. Since the ADC and FPGA and DAC are in the same FPGA block, the latency will be very less in this case. Next, we have a SIGINT or ELINT receiver. Here, the full Nyquist ADC acquisition from DC to 4.4 gigahertz will be done from the antenna onto the ADC. The ADC will run the channelization and demodulation. And some of the detection, signal analysis and detection will be done on the ARM core. We can store this data on the board itself for further processing or use the high-speed connectivity to move it to the processing units. So we can see on the right side the ELINT receiver unit designed by iWave. That is all from the software side. Following this, we'll have a quick Q&A session, requesting you to please post any questions that you might have, and we'll try to answer them. Over to you, Divya.
All right. Thank you, Abdul. Okay, let's take a look at Q&A. We see a few questions. So my first question is, what is the performance comparison of RFSoC versus Versal RF, David?
Okay, let me, I actually have a slide on that. I can show you. If you want to look at, comparing, somebody took the, one way we compare the Versal RF is to the Zynq UltraScale plus RFSoC Gen 3 because they're both general purpose parts. So if you take a look at the RFSoC Gen 3 and then compare it to the Versal RF series, either the 16XX devices or the 19XX devices, you can see that the amount of DSP compute is up to 19 times what we have in the RFSoC Gen 3. The actual sample rate is about 6.4x higher in the Versal RF, and then the RF bandwidth is a full 3x higher from 6 gigahertz to 18 gigahertz. And so when you think about it, if we increase the RF bandwidth by 3x and we increase the sample rate, you've got a lot more data that you have to process with, typically DSP functions. And that's why we increase the DSP ops so much by adding the hard IP. Okay, so I think that answers the question, Divya.
Thank you, David. So there's one more question. What are the BSP options available with RFSoC from iWave?
Let me take that question. So by default, the standard deliverable that we provide is based on Yocto BSP. Apart from that, we also support Pink BSP and the bare metal application. Divya?
Okay, we'll take one last question. So, how thermal aspects are taken care on SOM level?
Yeah, let me take that question. Yeah, so the SOM level, when you, as you can see here, so we provide a complete thermal solution, and the all key dissipating components are placed in the top of the SOM, and we provide a complete thermal solution for that, either as a fancying or a heat spreader or different other method like liquid cooling, all different type of thermal cooling we support for the sounds. I hope it answers.
Yes, thank you for addressing that question, Pradap. At this point, we are coming up on the end of our scheduled time. We have almost exceeded our time. We see that there are a few more questions in the Q&A panel that we couldn't get to answer today. Please be assured, we'll review all unanswered questions and reach out to you separately after the webinar. We'll also be sharing the webinar recording and presentation materials shortly. Before we wrap up, I'd like to thank our speakers for sharing their insights today and all of you for joining and engaging with us. Thank you once again for your time and have a great day. Thank you.